Welcome everybody. Let's talk about Avogadro's hypothesis. What Avogadro's hypothesis was that at a particular temperature and pressure, if you have the same volume, you have the same number of particles of gas. And so what this means is if I have a box with a particular volume, and I have, say, 3 of those boxes all with the same volume, if they are at the same pressure and they are at the same temperature, then they must have the same number of particles within each of those boxes. And there were a couple of things about this hypothesis. First, he said it didn't really matter what the type of particle was, what that identity was, it was just the total number. This makes sense because at a particular temperature, all the particles will have the same average kinetic energy, so we can relate that to the same motion. And if the pressure is the same, there has to be the same number of collisions. And in order for this to be true, for there to be the same number of collisions, there must be the same number of particles. And I'm going to emphasize again, it doesn't matter what the identity of those particles are, there just has to be the same number in the same volume. And with this, I want to talk about some different types of particles. We can have what are called monatomic particles, where each particle is made of a single atom, and those would be the particles in the box on the left. You can have diatomic particles, where each particle is made of 2 different atoms, either the same element or different. And you can also have polyatomic particles, where every particle is made up of 3 or more different atoms. So with Avogadro's hypothesis, he was able to make some predictions about the formulas of those particles, what chemicals actually were made out of. So he was looking at observations, and other chemists following him were looking at observations about how gases reacted. So for example, let's say they had 2 liters of gas, we'll call it gas A, and that reacted with 2 liters of gas B, and it formed 2 liters of a product gas. So we want to try to picture what's going on here. We know that in every volume that's the same, so we're going to say 2 liters is 1 volume, so each of the boxes on the screen represents 2 liters. Then in each of those, there must be the same number of particles. So if you have 2 liters of gas A, maybe there are 4 particles. The exact number doesn't matter. What's going to matter is that we're consistent. That means in 2 liters of gas B, there has to be also 4 particles. And that means in the product, there has to also be 4 particles because there's 2 liters of that product. Well, the only way to get 4 particles is to combine A and B, and they do have to be identical particles. So this tells us that the product is a combination of 1A and 1B in every particle. And so we've actually been able to infer what the product must be based on these ratios of gases that reacted. Let's take a look at another example. Let's say I've got 1 liter of gas A, and it combines with 1 liter of gas B to form 2 liters of product. Now remember, the rule is that every box must have the same number of particles in it. And when early chemists found this, this seemed really weird. How do you combine gas A and gas B and get just as much gas as you had before? How does that work? Well, it turned out that the way to explain this is to have both gas A and gas B be diatomic. Because then when A and B combine, you can still make 2 liters, in this case, of product, and each one will be an A and a B. So this was actually the first indication that there were elements that were diatomic, was experiments involving hydrogen and chlorine gas, and they were seeing this sort of relationship. So this pattern set the stage for chemists to be able to figure out what are our formulas, how are these compound or these chemicals reacting, and what are we making? Let's look at one final example in this video. So last one, which is going to again demonstrate how you can predict the formula of a product, says you've got 2 liters of a monatomic gas A. So let's call this A, and because it's monatomic, each particle has only a single atom. And then we have 4 liters of the diatomic gas B. So twice the volume, so 2 boxes, and it's diatomic. And therefore, because it's diatomic, every particle will be consisted of 2 B atoms. So again, in order to get only one volume, I have to have 4 particles. To evenly distribute all of these atoms in 4 particles, I'm going to come up with the formula 1A and 4 B's. And I would show that in writing that chemical formula by writing it as AB4. And so you'll notice I'm saying what's my element, I'm going to use its symbol, and then this number next to it is a little subscript, and that tells you how many of those elements you have in a single particle of that particular chemical compound, or element as the case may be. And so Avogadro's hypothesis gave a very powerful way to begin the investigation of what actually are all of the materials around us. And again, they started with gases because Avogadro's hypothesis says specifically that for a gas at the same pressure and the same temperature, if you've got the same volume of gas, you've got the same number of particles. So if you have twice the volume of gas, you have twice the number of particles. And this direct relationship between volume and particles provided a key for chemists to start understanding what was going on.